we now start module 4 of chapter 3. The topic is harmonic functions. We have already discussed about analytic function. Suppose f is an analytic function and f equal to u plus iv. Then derivative of f can be expressed in several ways. As for example, we can write del f del z is equal to del u del x plus I del v del y, that is equal to del f del x. Since f is analytic, it satisfies Cauchy-Riemann equation. So, using ux equal to vy and uy equal to minus vx, we obtain del f del z equal to minus I del f del y. Differentiating again from the first, we get del 2f del z2 equal to del 2f del x2, and from the second we get del 2f del z2 equal to minus del 2f del y2. From this we can get del 2f del x2 plus del 2f del y2 equal to 0. Since f equal to u plus iv, from this we get del 2u del x2 plus del 2u del y2 equal to 0 and del 2v del x2 plus del 2v del y2 equal to 0. This equation is known as Laplace equation. We define harmonic function as a function having continuous first and second order partial derivatives satisfying Laplace equation. Harmonic functions plays an important role in solving many engineering problems where Laplace equation is involved in analysis. After that, we will discuss harmonic conjugate and we deduce a relation between harmonic function and analytic function. After that, we will discuss Milne-Thomson method. By this method, we can construct an analytic function when either the real or imaginary component of the function is given. At last, we will provide some example related to this module. Now, we go to our slide. So, we start harmonic functions. A function u of x and y is said to be harmonic in a domain D if the partial derivatives del u del x, del u del y, del 2u del x2, del 2u del x del y, del 2u del y2 exist and are continuous in D, and if at every point of D u satisfies the partial differential equation del 2u del x2 plus del 2u del y2 equal to 0, known as Laplace equation. Now, we define conjugate harmonic functions. Suppose that u and v are two harmonic functions of x and y in a domain D which satisfy Cauchy-Riemann equations, that is del u del x equal to del v del y and del u del y equal to minus del v del x at every point of D. Then the functions u of xy and v of xy are said to be conjugate harmonic functions in D, and the functions uxy and vxy are said to be harmonic conjugate to each other. Now, we give an example. We consider the function f of xy equal to 3x square y minus y cube plus 1, and we show that this function is harmonic in complex plane. So, here the function is 3x square y minus y cube plus 1. Therefore, differentiating partially with respect to x with respect to y, we obtain f of x equal to 6xy, f of y equal to 3x square minus 3y square. Again differentiating, we obtain del 2f del x2 equal to 6y and del 2f del y2 equal to minus 6y. Since the second order partial derivatives of f are continuous and del 2f del x2 plus del 2f del y2 is 0, the function f is harmonic in the complex plane C. So, now we prove a result. There is an intimate relation between harmonic function and analytic function as shown in the theorem. The theorem is a function f of z equal to u of xy plus I v of xy is analytic in a domain D if and only if its real part, that is u of xy, and imaginary part v of xy are harmonic conjugate to each other. So, to prove the result, we use another result. The result is if a function fz equal to u plus iv is analytic in a given domain D, then the derivatives of all orders are also analytic in D. The result we will prove later. To prove the necessity, we first assume that f is analytic in D. Then the functions u of xy and v of xy are differentiable and they satisfy Cauchy-Riemann equations at every point of the domain D. The function f dash z is also analytic in D, being the derivative of an analytic function. Since f dash z equal to ux plus I vx, and that is equal to ux minus I uy, and also f dash z equal to ux plus I vx, that is equal to vy plus I vx. Here we use Cauchy-Riemann equations. So, from this we see that ux minus uy and vy vx are pairs of differentiable functions satisfying the Cauchy-Riemann equations in D. Therefore, we get del 2u del x2 is equal to minus del 2u del y2, that is del 2u del x2 plus del 2u del y2 equal to 0, and also del 2v del y2 is equal to minus del 2v del x2, that is del 2v del x2 plus del 2v del y2 equal to 0. Thus, each of the functions u and v satisfy the Laplace equation. Since f dash z is analytic in D, it is continuous in D, and so del u del x, del u del y, del v del x, del v del y are all continuous in D. Again we can write f dash z equal to ux plus I vx, that is equal to vy minus I uy. So, differentiating again we get f double dash z is equal to del 2u del x2 plus I del 2 v del x2 equal to minus del 2 u del y2 minus I del 2 v del y2 equal to del 2 v del y del x minus I del 2 u del y del x. Since f double dash z is analytic in D, it is continuous in D, and so del 2 u del x2, del 2 u del y2, del 2 u del x del y, del 2 v del x del x, del 2 v del y2, del 2 v del x del y are all continuous in D, and hence u and v are harmonic conjugate in D. So, now we prove sufficient part. So, to prove the sufficiency, we note that if u and v both are functions of x and y are harmonic conjugate functions, then in particular they have continuous first order derivatives in D and satisfy the Cauchy-Riemann equations in D. Therefore, the function fz equal to u of xy plus I v of xy is analytic in D. So, now we give an example. The function e to the power z, we put z equal to x plus iy. So, that is equal to e to the power x plus iy, and this can be written as e to the power x into e to the power iy, that is equal to e to the power x cos y plus I sin y, and this equals e to the power x cos y plus I e to the power x sin y. We know the function e to the power z is analytic everywhere in the complex plane. So, by this theorem we can say that its real part e to the power x cos y and imaginary part e to the power x sin y are harmonic in the entire complex plane. Now, we prove another result. Let u function of x and y be harmonic in some neighborhood of the point x0 y0. Then there exists a conjugate harmonic function v which is a function of x and y defined in the neighborhood, and also fz equal to u of xy plus I v of xy is an analytic function. So, we give proof of this result. The harmonic function u of xy and its conjugate harmonic function v of xy will satisfy the Cauchy-Riemann equations ux equal to vy and uy equal to minus vx. The function v of xy can be constructed from u of xy in two steps. Number 1, first we integrate del v del y, that is vy, which is also equal to ux with respect to y, treating x as a constant. That is, we obtain v of xy equal to integral ux of xy dy plus psi x, where psi x is a function of x only, and hence the partial derivative of psi x with respect to y is obviously 0. Secondly, we differentiate the above equation with respect to x. and we replace Vx by minus uy on the left side to obtain minus uy of xy is equal to d dx integral ux of xy dy plus psi dash x. Since u is harmonic, all terms except those involving x only is cancelled out, and a formula for psi dash x will purely be a function of x. The integration of psi dash x be used to have psi x, and this we will insert in first one to obtain v of xy, and then we obtain our desired analytic function fz, which is equal to u plus iv. Now we give a remark. If u is harmonic on D such that fz equal to u of xy plus I of v of xy is analytic, then v is called harmonic conjugate of u. Another one, we have the anti-symmetric property that v is a harmonic conjugate of u if and only if u is harmonic conjugate of minus v. This is because the function I into f, that is equal to I into u plus iv, that is equal to minus v plus iu is analytic whenever the function f is analytic. The function fz equal to z equal to x plus iy is analytic function. Therefore, v of xy, that is equal to y, is harmonic conjugate of u of xy, that is equal to x. However, the function g of z equal to y plus ix, that is equal to I into x minus iy equal to I conjugate z is nowhere analytic. From this we can conclude that if v is a harmonic conjugate of u in some domain, then u is not a harmonic conjugate of v unless u plus iv is a constant. So, now we consider another example. Prove that the function u of xy equal to 2x into 1 minus y is harmonic. Find its harmonic conjugate and the corresponding analytic function. So, here u is twice x into 1 minus y. So, differentiating partially with respect to x and y, we get del u del x equal to twice 1 minus y and del u del y equal to minus twice x. Differentiating again with respect to x and y respectively, we obtain del 2 u del x 2 equal to 0 and del 2 u del y 2 equal to 0. So, this gives del 2 u del x 2 plus del 2 u del y 2 equal to 0. Therefore, the given function is harmonic. Now, we find out Vxy, that is the harmonic conjugate of Uxy. Since u and v satisfy Cauchy-Riemann equations, del u del x equal to del v del y and del u del y equal to minus del v del x. Therefore, del v del y equal to del u del x equal to 2 minus 2y. Integrating this equation with respect to y, keeping x as constant, we obtain v of xy equal to twice y minus y square plus phi of x, where phi of x is a function of x only. Again, differentiating this equation with respect to x and using the relation del v del x equal to minus del u del y, we obtain phi dash x equal to twice x. By integrating, we get phi of x equal to x square plus c, where c is any constant. So, we obtain v of x y equal to x square minus y square plus 2y plus c. We consider another example. Find an analytic function whose real part is u, which is equal to e to the power minus x into x sin y minus y cos y. So, here u is e to the power minus x into x sin y minus y cos y. So, differentiating partially with respect to x and y separately, we get del u del x equal to e to the power minus x into sin y minus x sin y plus y cos y. Del u del y equal to e to the power minus x cos y plus y sin y minus cos y. Again, differentiating partially with respect to x and y respectively, we get del 2 u del x 2 equal to e to the power minus x minus 2 sin y plus x sin y minus y cos y, and del 2 u del y 2 equal to e to the power minus x into twice sin y minus x sin y plus y cos y. From this, we see that del 2 u del x 2 plus del 2 u del y 2 is 0. Therefore, the given function u is harmonic. So, let v be the harmonic conjugate of u. Then u and v satisfy Cauchy-Riemann equations, ux equal to vy and uy equal to minus vx. Therefore, we get vy equal to ux equal to e to the power minus x into sin y minus x sin y plus y cos y. So, integrating this with respect to y, keeping x as constant, we obtain v, that is equal to e to the power minus x into x cos y plus y sin y plus phi of x, where phi x is a function of x only. Now, we differentiate this equation with respect to x, and we use the relation Vx equal to minus uy, and from this we obtain phi dash x is 0. So, after integrating, we get phi x is constant c. So, we obtain v of x y equal to e to the power minus x into x cos y plus y sin y plus c. So, therefore, the corresponding analytic function is given by fz equal to u of x y plus I v of x y. So, just we put the value of u and v here, and we obtain our corresponding analytic function. So, another example, given that the function fz is analytic in a domain D, we have to prove that del 2 del x 2 plus del 2 del y 2 mod fz square, which is equal to 4 into modulus f dash z square. So, we assume that capital F is equal to mod f z square, that is equal to u square plus v square, where f z is u plus I v. Since f z is analytic in D, u and v are harmonic conjugate there, and so both u and v satisfy Laplace equation. So, therefore, we obtain del 2 u del x 2 plus del 2 u del y 2 equal to 0, and del 2 v del x 2 plus del 2 v del y 2 equal to 0. Now, del capital F by del x is equal to twice u ux plus v vx. Del capital F by del y equal to twice u uy plus v vy. Del 2 capital F by del x2 is equal to twice u uxx plus ux square plus vx square plus v vxx, and similarly we get del 2f del y2. So, from this, using the above equation and noting that u and v satisfy Cauchy-Riemann equation, we obtain del 2 capital F by del x2 plus del 2 capital F by del y2 is equal to 4 into modulus f dash z square. So far we have discussed about harmonic functions, conjugate harmonic functions. We also see that there is an intimate relation between analytic function and harmonic function, and the relation is if f equal to u plus iv is analytic in a domain D, then u and v are harmonic conjugate to each other. Now we discuss Milne-Thomson method. By this method we can construct an analytic function if either real or imaginary component of that function is known. Now we go to our slide. So now we describe Milne-Thomson method for constructing analytic functions when the real or imaginary component is known, and hence finding harmonic conjugates. So to discuss this method, we use the result if a function fz is analytic in a domain, then fz can be integrated in the domain using anti-derivatives. That is, by finding another function gz such that g dash z equal to fz. We prove this result in later. We assume that a harmonic function u of xy is given. We have to construct an analytic function fz equal to u plus iv. Therefore, u of xy and v of xy are harmonic conjugates, and hence they satisfy Cauchy-Riemann equations in every point of that domain. Since f dash z equal to ux plus I vx, and that is equal to ux minus I uy, we can write f dash z in terms of z, and the integration of f dash z then gives the desired function fz to some additive complex constant. So now we take an example. Construct an analytic function f of z in terms of z whose real part is given by u, which is equal to minus x cube plus 3x into y square plus twice y plus 1. So here u is equal to minus x cube plus 3x y square plus 2y plus 1. So differentiating this with respect to x and y partially respectively, we get del u del x is equal to minus 3x square plus 3y square and del u del y equal to 6xy plus 2. Therefore, f dash z equal to del u del x plus I del v del x, that is equal to del u del x minus I del u del y. Now we put the value of del u del x and del u del y, and this gives f dash z equal to minus 3z square minus 2i. So, integrating we get f is equal to minus z cube minus 2i into z plus c, where c is a constant. So, this gives our required analytic function. At the end of this module, we came to know about harmonic function, harmonic conjugate function, and the relation between harmonic function and analytic function. We also came to know to construct an analytic function if the real or imaginary component is given. Some problem were discussed. For more problem, please see the self-assessment part of this module. You can also consult any reference books for more details. This ends module 4 of chapter 3.